Hello, class. Today we're going to be talking about truth tables and equivalent statements. And a truth table is a logical way of determining the validity of statements, compound statements, really. So, let's talk about the conjunction P and Q. If I have a statement, and we're going to start with this example here. Let's say that P represents today is a weekday. And let Q represent today is sunny. Well, if today is a weekday and today is sunny, we could say that the statement P and Q is true, right? But what if today is Saturday and it's sunny? Could I say that this conjunctive statement is true? No, I couldn't. In order for a conjunction to be true, both parts have to be true. So, in my case, today is a weekday. That is true. Let Q represent today is sunny. And I'm recording this in April, Apple Blossom weekend. And it is sunny. How great is that? So, that is true. So if we're looking for the truth value of P and Q, I can say that P and Q is true because both my statements are true. For a conjunction is true if both P and Q are true. Now we have a truth table and we can use our truth table to show every possible outcome. Now let's say that P is true or P is false, right? P is going to be either true or false. What about Q? Well, what if P is true? Then Q could either be true or false. Or if P was false, Q can be true or false. And what this does is this gives me 4 possible outcomes. My 4 possible outcomes are true, 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 false, false, true, false, false. This gives me every combination of P and Q that we can have. They're either both true, they're both false. P is true, Q is false. P is false, Q is true. Those are the only 4 ways I can mix up the truth and falseness here. Falseness. Is that even a word? I don't know. Okay, so we're going to make a truth table. Half of the time, P is going to be true. The other half, P is going to be false. Well, if P is true, Q could also be true, or Q could be false. If P is false, Q could be true, or Q could be false. Now, for this statement P and Q to be true, we need both to be true. Otherwise, this is false, false, and false. Let's talk about the disjunction P or Q. And we're going to go back to this example. Today is a weekday. Today is sunny. Is P or Q true or false? Well, today is a weekday for me, and today is sunny for me, and we're going to say that P or Q is actually true. And we call this the inclusive disjunction. The inclusive disjunction, normally when you hear the word or, it's used in the context where you do your homework or you're going to be grounded for a week. And so it's exclusive where it's one or the other. Well, for our purposes, we're going to be using the inclusive disjunction, which says that it could be P, or it could be Q, or it could be both. Now, the truth of the disjunction, let's talk about this. The disjunction is true if P is true, Q is true, or both are true. So we set up our truth table. We have true, true, false, false, true, false, true, false, and I look at the or. If P is true and Q is true, P or Q is true. One of them's true, one of them's true. This is really the only exception. You get a false for the or statement if both statements are false. Let's talk about negations. We've talked about negations before. We talked about negations in 3.1. For a negation, you don't need two statements. P is either true or false. Not P is going to be the opposite. It's going to have the opposite truth value. So if P is true, not P is false. If P is false, not P is true. And do you want me to write down? Let's write this down. I would read this as not P. I would read this one as P and Q. I would read the one below it as P or Q. Okay. So let's do a couple examples. Let's do a couple problems. Let P represent 3 is greater than 1. That is 3 greater than 1? Yeah, it is. That's a true statement. We're going to let Q represent 5 is less than 9. Is that true? Yes, it absolutely is. Let R represent 8 is less than 8. Is that true? Nope. That guy's false. So what we can do here is we can substitute. When I look at this compound statement, this is P and R or not Q. What I'm going to do is I'm going to substitute the true, true, false in place of P, Q, and R. And then I'm going to evaluate this using the order of operations. So P is true. So it's true and false or not true. And all I did was substituted true for P, true for Q, false for R. So let's look at and. We said that and is true only when both are true. Otherwise, and is false. So this part right here, is that going to be true or false? Again, for the and, we need both, so this is false. Or, what's the opposite of true? False. And for our or statement, we need to have at least one of them be true for the statement to be true. In this case, we have false, false, false or false, which is false. Let's do another one. Right here. Okay, so I'm going to substitute the values for P, Q, and R, and I'm going to evaluate this using the order of operations. I'm going to give myself a little more room. I got to write small here. All right, so we have not, not Q is, I'm just going to slide this over so we can see. Q is true, so it's not true. Or, parentheses, R is false, and not P, that's not true. So order of operations says I start inside the parentheses. I'm just going to double check this. P is true, Q is true, R is false. So we start on the inside here. False and not true. That's going to be false and false. And I'm just going to go through and change one thing at a time. I ask my algebra students when they're using PEMDAS to just make one change at a time and take it slow and don't get ahead of yourself. Okay, I'm working in parentheses. False and false is false. I'm still working in parentheses. I have these braces here. Not true is false or false. False or false is false. And not false is true. So what this tells me is that this compound statement is true. This compound statement is false. And it really is, honestly, this really is an order of operations problem. Both of these are. Go ahead and flip your paper over. So we've talked about the number of outcomes when you have two statements. We said that you have 4 possible outcomes. If you just have one statement, you have 2 possible outcomes. When you have 2, you get 4. What if you had 3 and we added R to the mix? Well, this gives me all of the different outcomes for P and Q, and what I would do is I would say, okay, well, what if P is true? What if Q is true? Then R could be true or false. If P is true, Q is false, R could be true or false. True or false, true or false. And what that does is that takes me from one statement with 2 outcomes, 2 statements with 4 outcomes, 3 statements with 8 outcomes. What do you think 4 would have? 4 would have 16, right? So let's see if we can kind of nail this down here. So let's suppose I have one statement, and that statement is P. There are 2 possible outcomes. P is either true or false. Once I add a Q to the mix, now I have 2 statements. I end up with 4 outcomes like we did in the tree diagram. And I'm going to write P and Q. If I add a third one, P, Q, and R, now I have 3 statements. We saw that that was going to be 8 outcomes. Do we see a pattern here? 2, 4, 8. If I add an S, now I have 4 statements. This is going to double again. Because for every outcome I had from for all of the 8 different outcomes, when I add another statement, from here, S would either be true or false, true or false, true or false for each of these 8 outcomes. So we now have 16. In general, if I have n statements, I have 2 to the nth possible outcomes. The ones you're going to see most often are 2 statements or 3 statements. So P and Q, I have 2 statements. And as you're building your truth tables, you're going to start by listing out all possible truth values for PQ or PQR or PQRS and so on and so on and so on. So this can be true, true, false, false, true, false, true, false. The big idea here really is this. Half of the time, and I'm going to write down, we have 2 squared outcomes. Half of the time, P will be true. Half of the time, P will be false. We focus in on when P is true. Half of the time, Q will be true. Half of the time, Q will be false. If we look at the falses, half of the time, Q will be true. Half of the time, Q will be false. From there, we evaluate the validity of our compound statement. P, Q, and R. Now I have 3 statements. 3 statements is going to yield 8 outcomes. Of the 8 outcomes, half of the time P will be true. So I'm going to write true, 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 true. Half of the time P will be false. Let's look at when P is true. Half of the time Q will be true. Half of the time Q will be false. Well, if P is false, half of the time Q will be true. Half of the time Q will be false. And then I look at this. The last column is always going to be staggered. True, false, true, false, true, false, true, false. And this gives me every possible outcome or every possible combination of trues and falses for all 3 statements. So let's construct a truth table for the compound statement, not Q, and parentheses, not P or Q. Here I have 2 statements, so I'm going to begin by listing this out. This is true, true, false, false, true, false, true, false. We can treat this like an order of operations problem where we start inside the parentheses. And I look and I say, okay, well, inside these parentheses, the first thing I'm going to have to do is not P. So let's figure out what not P is. Not P has the opposite truth value of P, so that's going to be false, false, true, true. Now I can look at my parentheses, and that's going to be not P or Q. I'm looking at not P or Q, so I know for the or, it's one or the other or both. That's going to make this true, false, true, true. Now I'm going to look at this whole thing together. Well, no, actually, I need to look at not Q. So it's not Q and whatever this is. So let's see what not Q is. That's going to be false, true, because it has the opposite truth value of Q. And now I can finally pull it all together. Not Q and not P or Q. So I'm looking at this and statement. I'm looking in this column of not Q and this column here. And I need, for the and, we need both to be true in order for it to work. I need this to be true and this to be true. So that gives me false, 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 true. This would be my final answer. This is the truth table, or the value of the truth table for this compound statement. That's method 1, where you kind of look at it one piece at a time. Yeah, it's not my favorite method. It works. It works. I like doing this instead. I like method 2. This is how you're going to see me do it when we're in class. I have true, true, false, false, true, false, true, false. I'm just going to write my compound statement here. Not Q and not P or Q. And under each thing, I'm going to have a list of trues and falses, list of trues and falses, list of trues and falses. I'm going to spread this out a little bit, actually. And so we just go through with our order of operations, and we do one thing at a time. So if I look at not P is false, false, true, true. I do this first. Right? Just like we did in method 1, we did not P first. Now I'm going to list out what the truth values are for Q. That's going to be true, false, true, false. Now I can evaluate this OR statement. Remember, for OR, it's one or the other or both. For the OR here, we're going to have true, false, true, true. So I've got the left side done. Now I'm going to look at and see what not Q is. That's going to be my 4th step here. Not Q is false, true, false, true. And for the final thing is this AND statement. The AND statement is going to be determined by this not Q and the result of what we had in the parentheses. And if you wanted to draw a line through these just to show that you're not looking at them anymore, I would be okay with that. So AND is true when both are true. So this is false, 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 true. And this is where my final answer is going to be. Let's talk about De Morgan's laws. De Morgan says that if we have not P or Q, that is the same thing. That's an equivalent statement to, think of this, P or Q, that's one or the other or both. Well, what would negate that? That would be not P and not Q. So if it's one or the other or both, the only thing that would negate that is if neither were true. So it's not P and not Q. The other one, not P and Q. So let's think of what P and Q it means. P and Q is both of them, right? It's this one and this one. Both of them have to work. So to negate that, we would say that that is not one or not the other. And remember, the or is not one, not the other, or not both. That would be the or. I'm going to let you guys verify that these two hold. And let's just talk about how to apply De Morgan's laws to negate statements. It is summer, and there is no snow. I have two statements here. It is summer is one of them. There is no snow is the other one. Let's call it is summer P, and there is no snow. Let's let that be Q. So if I'm going to negate this, I'm going to negate P and Q. And I know that when I negate P and Q, that is equivalent to not P or not Q. I get that from De Morgan. Thanks, De Morgan. So let's negate P or negate Q. It is summer. To negate that, we can say it is not summer. Or there is no snow. To negate that, we would say there is snow. This is not P or not Q. Dasher or Blitzen will lead Santa's sleigh next Christmas. Okay. Dasher or Blitzen. We're going to let Dasher leading the sleigh be P. Blitzen leading the sleigh can be Q. Or is that, and I know from De Morgan, right? I know from De Morgan that if I want to negate P or Q, that is equivalent to saying not P and not Q. So how would I say not P and not Q? That would be neither of these guys, right? So we're going to say to negate this, neither Dasher nor Blitzen will lead Santa's sleigh. The neither Dasher nor Blitzen, that gives me the not P and not Q. Yeah, and you know what? That is going to wrap up. That's going to wrap up section 3-2. So thank you so much. Have a great day. Bye.